Okay, so now let's continue with the derivations of the solutions of the second order ODE that we discussed in the previous video for modeling level 2 example. Let's continue in here. So for this particular second order ODE, we have these particular solutions in here. Okay. Note that for this particular solutions in here, the boundary condition is used to get the value of these two constant, which at the moment we don't know. So we need to find it from the boundary conditions. So let's start and using the first boundary conditions. At x equals 0, t is equal t1. So what we need to do is we need to just put in this into this particular expressions in here. So in this case, the value of the t will be equal to t1 minus t naught, and then d, and then this one will be cos h, because x is equal to 0, so this essentially translates to 0, and then e sin h at x equals 0, then this will be 0. Now we know that this value of the cos hyperbolic of 0 is equal to 1, and then the value of the sinus hyperbolic of 0 is equal to 0. So then we can basically simplify further. T1 minus T naught will be equal to D. So essentially your D is equal to T1 minus T naught. The detail of the derivative of the cos hyperbolic and the sinus hyperbolic is given in the notes that is attached into your canvas. So I would suggest that you look into the notes to get the more detailed descriptions in there. So once we get the value of the D in here, let's substitute it into the D in here. So let me have a change into the color of the pen. So essentially we have this T minus T naught is equal T1 minus T naught cos h 2 hg k r x plus e, sorry, this one is not very clear, so I repeat again, plus e sin h root square of 2 hg krx. Here we can simplify further because otherwise this will be too long, so we can just simply abbreviate this term as m. Okay, and then we go into the boundary conditions 2 to try to solve for the value of e. So now we get the expressions of this t minus t naught. What we need to do further is we need to get the expressions for dt per dx. So we simply differentiate these equations in here. So if we differentiate these equations in here, we will have t1 minus t naught multiplied by m sin h mx plus e multiplied by m cos h m x, because the derivative of the sin h will be cos h, and then the derivative of the cos h will be sin hyperbolic. Okay, then we simply substitute these two terms in here. Okay, after having this expression, this will be 0 equal to t1 minus t naught m sin h m L2. Remember that our x in here is equal to L2 plus E m cos h ml2. Then we can move over one term into the left hand side. Then we can cancel these things out. Okay, and continue the derivations. E will be equal to minus T1 minus T0 sin h ml2 divided by cos h ml2. Then we continue again. Now we know the expressions for the E. Okay, now we put these expressions of E back into these equations in here. So if we do that thing, we should have T minus T0 will be equal to T1 minus T0 cos h mx minus T1 minus T0 sin h ml2 cos h ml2. Let me erase this thing a bit. Then this one will be multiplied by sin h mx. Okay, so I go ahead with these derivations. T minus T0 is equal T1 minus T0, and having a bracket in here, cos h mx minus sin h ml2 sin h mx over cos h ml2 then this one, if I can basically I want to simplify further, then this will be cos h ml2 cos h mx minus sin h ml2 sin h mx divided by cos h ml2. Then we can go into the definitions of the cos hyperbolic of x minus y is equal cos h x cos hy minus sin h x sin hy. So then we can simplify the term further. T minus T0 will be equal to T1 minus T0 cos h ml2 minus mx divided by cos h ml2. And we can have one more term, 1. So this one will be cos h m L2 minus x divided by cos h ml2. So this will be, after we solve using the two boundary conditions, we have a final expressions for our temperature in the rod above the solvent air interface. So you essentially have the expressions for the temperature in the rod from this point here through this point here. Okay, with that expressions of the temperature, what you can get next is the heat flow, or your Q basically. Your Q will be, so your heat flow through area pi r square at x equals 0 must be equal to the heat release into the atmosphere. So you have to go back again and see what do you mean by the Q. So you want to find the Q at this particular point in here at x equal 0. Okay, so let's go back there again, and then now we define what is Q. Q is equal to Qx at x equals 0 multiplied by pi r square. So this is the heat conduction, the area of the heat conductions at x equals 0. So this will be equal to, if we go and if we in the top, this one is just the Fourier's law of heat conduction at x equal to 0 pi r square. And then so if we go up in here, we can find the expressions of the dt over dx. So in here, dt over dx will be simply equal to T1 minus T0 divided by cos h ml2 multiplied by minus m sin h m L2 minus x. Okay, so that will be our dt per dx. Then essentially our Q is equal minus k pi r square, and then this one will be T1 minus T0 cos h ml2 minus m sin h m L2 minus x. Let me erase this one because this is too long, so I need to squeeze these things a bit. This will be minus m multiplied by sin h m L2 minus x at x equal 0. Then this one will be minus k pi r square minus m T1 minus T0 divided by cos h ml2 sin h ml2. Okay, these two can be scrapped. 1, 2, you have negative, and then you continue the derivations. Pi r square k m square divided by m T1 minus T0 tangent hyperbolic ml2, then continue again pi k r square to hg divided by kr, because you need to remember that basically if you need to remember that M, what we define M is if we go up on top, M in here we define M as a root square of 2hg per kr. Okay, so we need to be consistent with our term in here. Okay, so this one m square divided per m, so this m square will be basically this 2hg over kr. Okay, and then let's go back into these things again in here, and then this one will be t1 minus t naught multiplied by tangent h ml2 divided by m. And then these things in here, we can cross this with this, we can cross this with this. Okay, so this one is cross. Then we can continue again. This one will be equal to 2 pi r hg L2 T1 minus T naught tangent H ML2 per ML2. So if we go into the, if we can basically notice that the heat flow in here will be equal to 2 pi r hg L2 T1 minus T naught, and then we have this term in here which we called mu. So this term in here is something that we called an effectiveness factor. Okay, so if you look back and compare with your modeling level 1, we have this particular type of formula almost the same with this, except before we don't have this factor in here, the effectiveness factor. Okay, that particular if you go back into your modeling 1, then it's the same, this Q, but except we have the additions of this mu in here. So this modeling level 2 give us slightly different expressions of the heat flow. Okay, I'll stop my video in here because I try to limit everything to below 18 minutes. Thank you.